Hello. Okay, so uh, I guess people will join in a bit. Let's start. So I'm going to share my screen and okay. So apologies, the assignment is a little bit late. I'm still working on it. So this is the draft. So we're talking about electric potential and capacitors. And we start with the describing what electric potential is. And then we talk about more electric potential. Then we talk about capacitors and capacitance. And then you have the energy of a charged capacitor, energy capacitors in parallel and series, and finally charging and discharging of a capacitor. Have you done capacitors in school? Question. Yes, a few people, more people should join, uh, hopefully. No, you haven't done capacitors in school. Okay. Right. So let's have you done electric fields in school? Okay, makes sense. Right. So you know what? If you give me a moment, I'll just send a message to everyone that we have started, just in case. Mm. Okay. Yes, I'm guessing the weather is very nice today, and fewer people than normal. But I sent a message to everyone, so hopefully we'll get more. Okay, so then we can start from the beginning of what electric potential is. So, and first, I would like to talk about conservative and non-conservative forces. Do you know what a conservative force is? That's fine, and I did not expect anyone to know that. So a conservative force is a force that has the same work regardless of the path taken. Okay, so imagine a force moves you from point A to point B, and along the way, the force does work because work is force times distance, times cos theta, of course. But that's very simple. That's when you're moving a straight line. When you're not moving in a straight line, then it's slightly more complicated. But nevertheless, when you're moving from A to B, or you're moving through A to B taking a different route, the work done is the same. So if work done is independent independent of path taken, then the force is conservative. So what's an example of a conservative force? Well, gravity is a conservative force. Imagine you are in the field of gravity and you're moving from A to B. The work done by gravity is your change in gravitational potential energy. So work is the change in gravitational potential energy. So, and it doesn't matter if you move like this or you move like this, the work done by gravity is the same, or like this. Hey, does that make sense? So conservative is gravity. And electrostatic. So how do we show that electrostatic is conservative? Well, let's say you have a positive charge and you're moving from point A to point B. Imagine you're moving along this path. You're moving perpendicular to the field in a circle. So if the movement is perpendicular to the force, so the force is outwards, right? So the force is like this. If the force is perpendicular to the movement, what's the work done is 0. So the work done along path AC, so the work done along AC is 0. And then the work along CB is force times the distance between C and B. Or you can move from A to C in a different path. So for example, you could take this path, go from A to point D, and then D to B. And in this case, the work AD is 0. And the work CB is equal to the work along AD, because it doesn't matter as you move from A to D or you move from C to B, the work done is the same. And then the work done, and that means that the work done along path ACB is the same as the work done along path ADB. So electrostatic. An example of a non-conservative force. Do you think you can give me an example of a non-conservative force? They're also known as dissipative forces. Yeah, friction is a non-conservative force. Yes, friction. Very good. Because if you take a longer path, you do more work because there's a bigger distance. So yeah, and elastic potential. Elastic potential is actually a conservative force because the work done depends on just the extension. Yeah, it doesn't depend on the path taken. And conservative means they conserve, so they have potential energy attached to them. That's why they're called conservative. They conserve energy. Um, Another easier explanation of a conservative force: if you throw something up, it will fall back down, right? You throw it up, it falls back down. It also happens in an electric field as well. If you throw something against the field lines, it will come back. Friction doesn't do that. If you throw something onto the ground, the friction stops it, but doesn't accelerate it back. So gravity stops the object and then accelerates it back down. Friction stops the object and doesn't accelerate it back down. Okay. And yeah, there's a funny story when there was a physics exam at my university, and the professor gave grades into a special book. So every student carried a special book. I think I still have it, but anyways, and you get a grade in your book. And so the professor said, "Okay, you don't know anything. Okay, tell me, is friction a conservative force or not?" And the student says, "Conservative." And he says, "Okay, I'll take your book and I'll throw it under the door, and if it comes back, I'll give you a C." And he threw the book, not expecting it to come back. But there was somebody on the other side of the door. They said, "Oh, there's a book. What do I do with it?" And they swing it back. So yeah, so the student got his C. Anyways, okay. How much work is required to bring together three charges into the corners of a square of side length A? The charges are very far from each other. So there's an imaginary square. And we need to bring three charges. Because initially so we have three charges. They're very far away from each other. What we need to do is we first need to bring the first charge into the first corner. Now, the first charge does not experience any force because as we move the charge, then just it's a vacuum. Yeah, there's no work. So zero work is done bringing the first charge. Zero work is done bringing the first charge. Because as the force is zero. Now the second charge, why am I doing work bringing the second charge in? Can somebody explain or suggest? Why am I doing work bringing the second charge in? Yeah, because it will be repelling. Yes, it will be repelling from the first one. So I have to push it against the field, right? Because the first one will try to push it away, so I do work bringing it in. And okay, so I need to calculate the work done. You will see that the potential energy, electrostatic potential energy, static potential energy between two charges is U, and it's equal to Q1, Q2 divided by 4 pi epsilon naught R. Okay, so this is the potential energy between two charges. So if this side of the square is A, then the potential energy of this charge, potential energy, is equal to Q, so it's Q squared divided by 4 pi epsilon naught A. That's the potential energy of this charge. That means the work done bringing the second charge, work done bringing this second charge is Q squared divided by 4 pi epsilon naught A. Now, finally, we need to bring in the third charge. So, sorry, you might be not convinced with that formula. So let me show that. Let me prove that to you. This is all very nice. This is the result we're aiming for. But if I were you, I would be totally unconvinced. So the charge on this charge is Q. The charge on this charge is Q. There's a force between them. And the force is equal to 1 over 4 pi epsilon naught Q squared divided by R squared, where R squared is the distance between them. R. And imagine this charge moves a small distance dr. So the charge moves a distance dr. Then the work done is dw, is a small amount of work. So it's a small amount of work to move the charge a small amount. The work done, dw, is the force multiplied by dr. Or in other words, 1 over 4 pi epsilon naught Q squared divided by R squared, dr. There is a catch though. dr is negative, but dr is negative. It's negative because R is decreasing. If we move closer, the R is decreasing as R is decreasing. Let's see. Obviously, the work is positive because we're pushing against the force, so we just have to put a minus in, minus here. Okay, and now we can integrate dw, the integral of dw. If we move at the beginning, we've done 0 work. At the end, we've done w work. Minus 1 over 4 pi epsilon naught. That's a constant, so we can take it out of the integral. Q squared is also a constant. So we have the integral of 1 over r squared. We start at a distance at infinity. We're very far away, and we finish when r is a, dr. So now we can integrate this. The left-hand side is just w. This is minus q squared over 4 pi epsilon naught multiply. The integral of 1 over r squared this is r to the power minus 2. So minus q squared over 4 pi epsilon naught infinity a r to the power minus 2 dr. And the integral of r to the power minus 2 is minus 2, is r to the power minus 1 divided by minus 1 between limits infinity and a, and that makes it minus and minus cancel, and we get q squared over 4 pi epsilon naught. Okay, let's keep the minus for now. Minus 1 over a plus 1 over infinity. 1 over infinity is 0. And we have this multiplied by minus a, which makes it q squared over 4 pi epsilon naught a. That is the work done, and hopefully I managed to convince you. Right? How convinced are you on a scale of 0 to 10? Okay, this is the work done, moving the second charge to the second corner. Okay. Now, I won't I don't think I'll do the integral for the third one. I'll just use the potential energy. Let's label the charge as charge 1 and charge 2. Now the third charge goes here, and the potential energy of this charge comprises of two things: the potential energy due to charge 2, the potential energy due to charge 2 plus the potential energy due to charge 1. And since we are in distance a away from charge 2, that energy is q squared divided by 4 pi epsilon naught a. But this charge is the distance square root of 2a away, which is plus q squared divided by 4 pi epsilon naught square root of 2a. So the total work done is the work done moving the second charge into position 2 plus the work done moving the third charge into position 3. So is q squared over 4 pi epsilon naught a plus q squared over 4 pi epsilon naught a plus q squared over 4 pi epsilon naught square root of 2a. Now, then you can add them. So I'm going to, what can I do? Multiply both sides by square root of 2. So square root of 2, it becomes 2. And if I multiply this by 2 and then multiply this by 2, 2, 2, so it's 4 plus square root of 2 q squared divided by 8 pi epsilon naught a. And that's the answer. You will have an extremely similar question right in here. Question 3. How much work is required to bring together charges Q1, Q2, and Q3 to the corners of an equilateral triangle of side length A? The charges are initially very far from each other. So hopefully you'll manage to do this question. All right, let's move on. Ooh, More people have joined. That's lovely. What is electric potential? Demonstration with electric field hockey. Electric potential is defined. Electric potential is the work done per unit charge moving a small positive charge from infinity to a given point in the field. Okay, that's the definition. The potential difference is the work done per unit charge moving a small positive charge from A to B. Why am I doing this? Potential difference. This is another important one. Potential difference work done per unit charge moving a small positive charge from A to B. There has to be a negative sign from B to A. From B to A. The potential difference between, and that's VA minus VB. So VA minus VB is moving from B to A. So it's the other way around. So, but it kind of makes sense because if you are moving a positive charge, you're doing work moving it from a low potential to a high potential. Potential. So I'll try to make it as simple demonstration as possible. So this is a charge. This is a positive charge. Trace. Okay. This is a charge. And this is a field. This is a field produced by a point charge. Field of a point charge. If you, okay, yeah, that's what I'm trying to do. Infinity to a point again. Imagine at infinity, you have a small positive charge. What you want to do is you want to move this positive charge from infinity all the way to some point here. So move from infinity to point A. So let's say work done moving a charge P, well, Q, charge Q. Work done moving Q from infinity to point A. A is WA. Does that make sense? So you're moving from infinity, you're moving to point A. And we've already seen that that work is Q divided by 4 pi epsilon naught A, where A is this distance. A. The potential, electric potential at point A is VA, is the work done per unit charge, so divided by Q. And if you divide WA by Q, you get Q divided by 4 pi epsilon naught A. So this is the electric potential around a point charge. VA equals Q divided by 4 pi epsilon naught A. What does that mean? That means to move a charge from very far away to point A, you need to do work. But that also means if you place a charge at point A, it will have energy. How can we tell that it has energy? Well, let's have a look. Can I zoom in? I'm not sure I can zoom in. No. So if I place a charge into the field, so the red charge produces a field, and the black charge is the small test charge. And if I release it, it will fly away. So we say that the black charge has potential energy. And we can clearly see that it does. It's something like this. If you does Desmos do 3D? It must do 3D calculators. Desmos. .3D. Ah, lovely. Z equals let's just do 5 divided by the distance from is going to be square root of x squared plus y squared. You can visualize it like this. So the Z is the potential. So the closer you are to the point, the more potential energy you have. So potential is the height above ground level. Potential is height is similar to height above ground. If you place a ball right here, it has potential energy. If you release it, it will roll down. And the same reason why this charge is placed into a field. So the field has potential, declining potential. And you see the potential gets smaller as distance gets further away, the potential gets smaller. So yeah, if you place a charge, it will roll backwards. A negative charge will create a negative potential. So just like this. So a positive charge would simply roll towards a negative charge. And that's negative potential. Field potential around a negative charge. So this is the potential around a negative charge. V is equal minus Q over 4 pi epsilon naught R, where R is the distance from the center. So this means a negative charge in the center, and there's a positive charge in the center. Does that make sense? Does that help you understand? Do you think you have a sort of intuitive understanding of potential now? Yes? No? Okay. Oh, yes. Yeah. Let's place two charges and see what happens. Let's place let's say two positive charges. Two positive charges. Now, you would think that the field cancels out. Yes, the field cancels out. But does it mean that it has zero potential? Of course not. Let's see what happens to the charge when I release it. So at first it struggles a little, doesn't know which way to go, doesn't know which way, and then suddenly it just starts flying. You could visualize it like this. Plus um, it's like this. We have two charges. It's like this. And if you're in between the two charges, you're in the midpoint. You're in the midpoint, and you still have high potential. So you might balance for some time there, and if you really close, if you're really centered, but then eventually you will roll off the side, and that's what's going on in here. So two charges. Yeah, it's an unstable equilibrium, exactly. Now, if I do this, if I have two charges and a negative one, Okay, so that would be this situation. So it's rolling from here, it's rolling on this side and then rolling back, rolling back, rolling back. Now, of course, this is kind of this is more like infinity, but let's say it's we can imagine it's finite because of course we understand that we don't have infinitely strong I wonder if we can rectify this, if we can do plus 0.1, 0.2, 3. Ah, that's better. Plus 0.4. So I need to just to add some 0.4, 0.6, 0.7, 8. Okay, that looks much better, right? Although it is infinite technically, but we don't have to assume that. So it goes rolls to the side and then rolls back, and it keeps balancing around the negative charge. You can do all sorts of things. You can shoot and then cause it to go in circles. Oh, doesn't like it. Okay. 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 So you can get it to move in circles. So this is effectively going around this bit over here. So that's quite fascinating. Okay. Anyways, I've went off track for quite a while. Yeah. So this is the idea of electric potential. When you go from infinity to a point, you do work, and yeah, the work done per unit charge is defined as electric potential. And okay, and this is very useful when you talk about the closest approach, for example. Problem 4. Calculate the distance of closest approach of a proton traveling at 2 times 10 to the minus 6 meters a second to a copper nucleus with 29 protons. Assume that the copper nucleus remains stationary. So what's going on here? We have a proton which is traveling at some speed, which is 2 times 10 to the 6 meters per second. And there is a large copper nucleus. So copper nucleus has 29 plus 29 protons. We assume that the copper nucleus remains stationary. Okay, so it's basically stationary. The proton will travel towards it, but it will slow down as it is repelled. It will slow down and it will eventually stop before accelerating back. This is the Rutherford's experiment, although Rutherford used gold atoms. So he was shooting alpha particles at a gold atom and they bounced back. And you can calculate the distance of closest approach. Let's call it A. A is the closest a proton can get to a copper nucleus. Copper nucleus. Okay. We remember that the potential energy energy is Q1, Q2 divided by 4 pi epsilon naught r squared is the distance between the particles. So that means it's charge of the proton, multiplied by the charge of the copper. It has 29 protons, so it's 29Q divided by 4 pi epsilon naught a squared, where a is the closest approach. Okay. The kinetic energy of the proton is, of course, 1/2 mv squared. So all the kinetic energy of the proton converts to potential energy, to the electrostatic potential energy. So that means 1/2 mv squared is equal to 29q squared divided by 4 pi epsilon naught a squared. And we can work out a is equal to 22 times 29q squared divided by 4 pi epsilon naught m v squared, and take the square root of that, and that should be 2 times 29 times the charge of a proton is 1.6 times 10 to the minus 19 squared divided by the 4 pi epsilon naught is 8.85 times 10 to the minus 12 times the mass of the proton. Mass of the proton is 1.67 times 10 to the minus 27 times velocity squared, which is 2 times 10 to the 6 squared. And hopefully we get some, so we get places. So square root square 2 times 2, 9 times 1.6 times 10 to the minus 19 squared divided by 4 pi times 8.85 times 10 to the minus 12, 1.67, 10 to the minus 27 times 4 times 10 to the 12ths, which gives us 1.41 times 10 to the minus 6 meters, which is 1.41 micrometers. Okay, that is bigger than I expected. Honestly, I assumed that it would get close, well, at least somewhat comparable to a nucleus, but no, it's actually much bigger than an atom. I don't know, maybe I got the calculation wrong, but if you double check my calculation, please do, if you manage to. But yeah, it's a very big answer. It's much bigger than an atom, so I've got doubts about that answer. Or maybe the people who came up with that question didn't actually consider that. That sometimes happens. Yesterday I found an A-level question where it said radon has 86 protons. Calculate blah 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 blah. And then I was like, wait a second, it doesn't have 86. It's 88. Or sorry, maybe it's the other way around, but they got the proton number wrong. Just yeah, random A-level question with the wrong number of protons. So yeah, proofreading. Anyways, two charges are Q and minus Q are placed a distance d apart. Find the position of where the field is 0 and where the potential is 0. So a positive charge and a negative charge, and this is plus Q and this is minus Q. Find the position where the field is 0. Or is there such a position? Don't think there is. Okay, let's make it 2q. 2q and minus 2q. Right. So find the position where the field is 0. The field is 0. I think I'm overcomplicating things. No, let's not do that. So there's no position. Sorry, there's no position where the field is 0 except infinity. Yes, the field is 0 at infinity because at any point the fields would add up. So for example, at the midpoint, the electric field due to the positive charge is like this, E1. And the electric field due to the negative charge is in the same direction, E2. So at the position in the midpoint between them, the two on the route to the equation on the Desmos graph. We're talking about field, not the potential at the moment. So at the midpoint, field is not 0. Not 0. It's actually E1 plus E2. They add up. They produce a maximum field, if anything. Not maximum, but just they produce a large field in the center. So that would be what's that? If this is a d apart, so that's the distance d. So that is q divided by 4 pi epsilon naught d over 2 squared times 2. So 4, that's 8, 2. So 2q over pi epsilon naught d squared. But the electric field is a vector. Electric field is a vector. But potential is a scalar. And that means it doesn't have direction. The field, the potential around a positive charge is positive, and the potential around a negative charge is negative. So at the midpoint, the potential is equal to the potential due to charge 1 plus the potential due to charge 2. So electric field is that. It's a vector sum. But the potential is a scalar sum. So that's going to be q divided by 4 pi epsilon naught d over 2 plus minus q over 4 pi epsilon naught d over 2, which is 0. So the potential at the midpoint between two charges is 0. That means you need to do 0 work to move from infinity to that point. But that also means if you release a point from that, if you release a charge from that point, at infinity, it will have 0 energy. So let me explain. To move, 0 work to move from infinity to the midpoint. Also, 0 gain in kinetic energy as it moves from midpoint to infinity. It kind of makes sense if you look at the midpoint, the potential is exactly zero. The potential is exactly zero at the midpoint. That means if you are standing here and you release from that point, when you reach infinity, you have zero speed. Let's see if that actually can be demonstrated. So what I'm going to do is I'm going to place a negative charge somewhere here. And I'm going to place a positive charge at exactly the same distance over here. And when I release, look what happens to the puck. So it starts off really quick, but as it goes further away, it slows down, slows down, slows down, slows down. Because there's a very small force, the attractive force between the attractive force to the negative charge is slightly more bigger than the repulsive force from the positive charge. So the charge will keep slowing down as it moves away, and at infinity, it will stop. Stop. Okay, then what does it mean that at infinity it will stop? Technically, that means it will never stop. It has just enough. At infinity, it will stop. That is just a fancy way of saying. It is the fancy way of saying it has the minimum necessary speed to never return. It has the minimum speed to never return. So at infinity, it will stop and never come back. There's no such point as infinity, but yeah, but it has the minimum speed never to return. If you studied cosmology, that is what the critical density of the universe is. That the universe will keep expanding, 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 but it has the minimum necessary density just to never to collapse. And yeah, but it will never. It will not expand infinitely. Neither it will collapse. It will grow to a certain size and just stop, sort of. Okay, so hope that makes sense. Okay, find the electric potential charge of a shell and a charged sphere. Oh, just let me check something. Field and potential of a charged shell and a charged sphere. So a charged shell is literally what it is. It is a very thin, positively charged shell. So when you're outside, you treat the shell as a point. Outside, treat the shell as a point charge. charge. And that means that the electric field is Q, where Q is the charge on that shell, Q divided by 4 pi epsilon naught r squared. And the potential, we already know, is Q divided by 4 pi epsilon naught r. But inside is much more fun. Gauss's law, and you've studied Gauss's law in the previous assignment, says that the electric field inside a shell is 0. Because all the electric fields from all the charges, they cancel each other out because it is a vector. But the potential, because we know that the electric field is defined as the rate of change of the potential with respect to the distance. But because the potential, this is 0, that means V is constant. V has to be constant because the derivative of V is 0. And E is the derivative of V. But if V is constant, that means it's the same as it is at the surface. Same as at surface. And at surface, we already know it's Q over 4 pi epsilon naught r. So we can sketch the graph. We can sketch the graph. So this is the electric field. And this is the distance. This is the surface of the sphere. This is the radius of the sphere, r. And we know that the electric field inside the sphere is 0. And then at the surface, it is Q divided by 4 pi epsilon naught r squared. And from here, it behaves as 1 over r squared, 1 over small r squared. The electric potential the potential at the surface. The potential at the surface is Q divided by 4 pi epsilon naught r, but it is constant inside the sphere, inside the shell, and then it falls as 1 over r. So somewhat less dramatic. So that's it. That's how you draw. Now we have a sphere. What's the difference? Well, the difference is that in a sphere, the charge is not located at the edges. The charge is uniformly distributed. Charge is uniformly distributed. So now it's a different situation. So this is so outside, nothing's changed. Outside, it's the same thing. So this is the electric field, and this is the potential. So outside, it is 1 over r squared. And here it's 1 1 over R. But inside, now Gauss's law says that the Gauss's law says that the electric field is only due to the charge what is below. So if you're sitting at point A, if you're sitting at point A, only the charge closer to the center of the sphere than A counts. Everything else, the field cancels out. And this works out very nicely, and this has been shown in the previous assignment, that it will be like this. It's a linear thing. It's a linear distribution. So it's going to be electric field inside the sphere is going to be R multiplied by Q divided by 4 pi epsilon naught R cubed. Right. Please take this without proof for now because we're limited in time. But hopefully you've seen that in the previous assignment. And now V. But we know that electric field is the derivative dV dt. That means if this is the derivative of V, and it's a linear function, then V must be a quadratic function. So it's going to be like this. Uniformly. Sorry, of course. I'm just talking nonsense. Apologies. I was wondering, no, that doesn't make any sense. Of course, because the gradient is still positive for E is positive, right? That means dV dt is positive. So it's not going to be like that. It's going to be first of all, it's minus. It's minus dr. Sorry, minus dV dr. And because it remains positive, so it goes like this. That makes much more sense. Okay, that is the potential at the center. That is the potential at the center, and yeah. KQ over R. So this is Q over. This is Q over 4 pi R squared. This is Q over 4 pi epsilon naught R. And this is actually 1.5 times the potential at the sphere. So the potential is higher. So that's going to be 3q over, well, let's say 1.5. Let's call this v of v0 at the surface, and this is 1.5 v0. Right. Okay. And next, flat capacitor and capacitance. Imagine you have two plates, two very large flat plates. So like two sheets of paper. And they're both charged, and the charge density, area charge density, is plus sigma on one plate and minus sigma on another plate. And if you remember, the electric field from an infinitely charged plate is sigma divided by 2 epsilon naught. Is the field from an infinite plate. That is derived from Gauss's law. And that means that this plate produces a field in that direction. And it's independent of the distance, by the way, which is very peculiar. It's independent of the distance from the plate. And a downwards field like this. Whereas the bottom plate produces a field in that direction. And a field in that direction. It expands beyond. So it's here as well. And the red field expands to here as well. And you can see that these two fields, because they're the same, they cancel out. So there's no field. And here, these two fields cancel out. No field. And that means that in here, the electric field is 2 times sigma over 2 epsilon naught, which is just sigma over epsilon naught. This is the electric field between two infinitely large plates. Does that make sense? You have two plates, they're producing electric fields, but they get outside above the top plate and below the bottom plate, they cancel out. And in between, they add up to create one strong field. And this is what we called a uniform electric field. So it's a uniform field. Uniform field. Okay. Capacitance. The electric potential, sorry, let's start with electric potential. So once again, we have two plates. One has a charge plus sigma minus sigma. That's not the charge, that is charge per unit area. So sigma is charge per area. And there's a field between. Let's say we want to move from point 0 to point D, where this is the x-axis. The potential difference V between 0 and D, 0D, is the work done per unit charge moving from 0 to D. So it's a minus the integral of E dx of E dx. Right. Now E changes, so x changes from 0 to D, so you're moving from 0 to D. But the electric field is minus sigma over epsilon naught. Minus because it's pointing downwards. Minus is downwards. And we sub that in, minus integral minus sigma over epsilon naught dx, 0 from D. Sigma and epsilon naught are constant, so sigma epsilon naught bracket 0 to D dx. And if you take this integral, it's going to be sigma D epsilon naught. So that's the potential difference between two plates of the capacitor. And now we have the capacitance. Capacitance is defined as C equals Q, the charge on each plate, divided by V. But remember that sigma is Q over area, so Q is sigma times the area of the plates. So it's sigma times the area of the plates divided by sigma D over epsilon naught. Sigma cancels, and the capacitance of a capacitor is A epsilon 0 divided by D. This is the capacitance of a flat capacitor. What does that mean? Well, I've got a box of capacitors, as everyone, I think. I mean, who doesn't have a box of capacitors? This is a capacitor. Why is it cylindrical? Well, it's flat. It's just what they do is they take two parallel plates, they put them together, they put a dielectric in between so they don't actually touch. So they put something in between, and then they roll them into a tube. They roll them into a tube, and that's very roughly how you get a capacitor. So a capacitor is two plates and two connections, of course. All right. The capacitance of this capacitor is 100 microfarads. 100 microfarads. What does that mean? Capacitance example. So the capacitance is 100 microfarads, and the capacitor is used to store charge. So if you connect the capacitor to a battery, it will get charged, and the capacitance is Q over V. Capacitance is Q over V. And it says V is 50 volts. And that means from Q is equals voltage times the capacitance equals 50 volts times C, which is 100 times 10 to the minus 6 farads, which gives you 50 times 100 times 10 to the minus 6, 5 millicoulombs of charge. So the capacitor carries 5 millicoulombs of charge. So each plate of this capacitor, so the capacitor contains 2 plates, and that means we can put 5 millicoulombs of charge onto this plate and minus 5 millicoulombs of charge onto this plate. We could potentially put more, but that means the capacitor will break. What happens when a capacitor breaks? Well, the electric field between them becomes so strong that you have a spark between. Okay. So if you well, let's look at capacitors. FET RLC circuit. So if you take a capacitor and you take a battery and you connect it, you connect the capacitor to a battery, and then you connect it to a light bulb. You need a switch. If you switch this switch on, you can see that the capacitor is now charged. You have a positive charge on the top plate and negative charge on the bottom plate. And now if you connect the capacitor to a light bulb, the charge will flow through the light bulb, the capacitor will discharge, but the light will work for some time. And you can measure the current. So charge the capacitor, and now 3, 2, 1, go. And you can see the current decreases as the capacitor discharges. So that's what the capacitors are used for. Right. Okay. And now you have the next problem. Sorry, the capacitance of a capacitor depends on the area and the distance between them. So if you look at the capacitor and you click on the capacitor, if you want to reduce the capacitance, you get the plates further apart. And that corresponds to this. If you get the plates further apart, the distance between the plates, it gets bigger, the capacitance decreases. And if you want to increase the capacitance, you can also increase the area. So FET capacitor lab. So here you can move this capacitor lab, you can move the separation and you can increase the plate area. So this increases the capacitance and that, that reduces. So if you charge, the capacitor and disconnect the battery, so you have 1.5 volts on the plates, but if you move them further apart, that voltage increases. And if you change the area, if you make it smaller, the voltage increases. You make it bigger, the voltage decreases, because we have a bigger capacitance on the capacitor. The next problem is just capacitors in series and parallel. It's very similar to resistors in series and parallel, although the other way around. Capacitance in parallel is just adding. Capacitors in a series, you do the same thing that you do as parallel resistors. So I'm not going to stop here. It's fairly straightforward. Charging a capacitor, that's the interesting one. I will rush through this, unfortunately, because I'm running out of time. So that's what happens here. Like, imagine I have a resistor and I have a capacitor. Forget about this bit. We don't need this. So I want to charge a capacitor. So, oh, I need a resistor. Sorry, resistor. Okay, I'm charging a capacitor through a resistor, and okay, and look what happens to the current. The current drops as the capacitor charges. And if I put the voltage chart, voltage on the capacitor, once again, so, oh, I need to discharge the, okay. Need to discharge the capacitor. Right, okay, so if I start charging the capacitor, you can see that the voltage increases and the current decreases. So I want to know what that equation is. So charging a capacitor. So I have a battery, I have a switch, I have a resistor, and I have a capacitor, C. Now, the battery is EMF, the resistor is R. So the current flows, when I close the switch, a current flows and charges the capacitor. And I know that the capacitance is charge divided by voltage. That means the voltage on the capacitor is Q over C. Q over C. Right, excellent. I know that the voltage on the resistor is IR, and the voltage on the capacitor is Q over C. So I write Kirchhoff's second law. The EMF of the battery is the voltage on the resistor plus the voltage on the capacitor. Right, EMF is equal to voltage on the resistor is IR plus Q over C. But then I remember that the charge is dQ over dt. So the current is the rate of change of charge, is the rate of charge. So I plug that into here. EMF is dQ dt times R plus Q over C. Now, if I can rearrange this because I want to separate Q, so I multiply everything by C, and then I subtract Q. So C EMF minus Q equals R dQ dt. Then I multiply everything by dt, multiply by dt, and divide by C EMF minus Q. So I get dt equals dr dq over C EMF minus Q. All right, so now I can take the minus out. So R dq over Q minus EMF capacitance equals minus dt. And now I can integrate from charge from 0 to Q final and time from 0 to t. And then if I integrate this, this is going to be R logarithm modulus Q minus EMF C equals minus T. So ln Q minus EMF C equals minus T over R. EMF CRQ EMF CR, yes. Apologies, of course. CR, 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 CR. Thank you. And then, yeah, if I take the logarithm between 0 and q, I get logarithm q minus EMF c minus logarithm minus EMF c equals minus t over CR. So it's the modulus. So I know that Q will always be less than EMF C. So it's logarithm EMF C minus Q. And mine divided by EMF C equals minus T over CR. And finally, EMF C minus Q over EMF C is EMF C is equal to E minus T over CR. Sorry for rushing this. I really have to go. And finally, I can express Q is EMF C minus EMF C E minus T over RC, which is EMF C 1 minus E minus T over RC. And that is the correct equation. So Q is the final charge, which is EMF C, 1 minus EMF E minus T over RC. And that's the charge on the capacitor as the capacitor charges. All right. So thank you for your attention. I really have to go. I'm quite late. And yeah, so see you in 2 weeks' time for some exciting equations and inequalities. So see you all. See you all. See you all then.